Hello, Algebra 2. Today your title for your notes is 13.1 Geometric Sequences. This starts our new module, Module 13, which is over exponential functions. And Module 13 also begins our last unit of the year, which is Unit 6, over exponentials and logarithms. So to start with Module 13, we're going to be looking at exponential functions. And 13.1 is geometric sequences. And what we're going to learn here in just a second is that geometric sequences are exponential. And so today's lesson is looking at exponential functions as a pattern and how we can develop a rule for them. Okay, so to start off, we have two types of sequences. And one of them you might remember from Algebra 1, and that's called an arithmetic sequence. Arithmetic. And some characteristics that makes a sequence arithmetic is that it has a common difference. Right? And it's also linear. Like if we were to graph it, it would be linear. An example of an arithmetic sequence would be the sequence maybe like 1, 4, 7, 10, and so on. What makes it arithmetic is that to go from one value to the next, I add 3 to get to each new value, and this is called the common difference. We said that arithmetic had a common difference, and so in this case, that common difference would be 3. But another example of an arithmetic sequence is, what if I had the sequence 15, 10, 5, 0, -5, and so on. This would be still arithmetic because to go to each new number, it's the same value, and it would actually be subtracting 5 this time to get to each new value. And so we would say that the common difference would be -5. Okay, but that's not going to be our focus of today's notes. We said our focus was geometric sequences, but we still want to be able to recognize if something is arithmetic or not. Really, if something's geometric, and if it's not, then what is it? Okay, so we're going to focus on geometric. And what makes a sequence geometric? Let's highlight that. So instead of a common difference, geometric sequence has a common ratio. And it's actually not linear, but instead it's exponential. And it can be either growth or decay, which is something we'll talk about later. Growth or decay. So examples of geometric sequences would be something like 5, 10, 20, 40, and so on. So even if you did not know what a geometric sequence is, by looking at this sequence, sequence of numbers, could you tell what we're talking about when we say it has a common ratio? I can see that to get to each new number, I'm going to multiply by 2. And that's what a common ratio is. You're multiplying by the same number. So this one would have a common ratio of 2. All right, another example. I have the sequence of numbers 6, 3, 3/2, 3/4. So to get to each new number, what do? We could say we divide by 2, but to keep our common ratio consistent and representing the same thing, we would say we would multiply by 1/2 to get to each new value in our sequence. Multiply by 1/2. And so my common ratio, because my common ratio represents what I'm multiplying by, would be 1/2. Okay. All right, so we now know what a geometric sequence is. And our notes today is going to focus on if we know something is geometric, how can we write an equation for it? How can we write a rule for that geometric sequence? Okay, so the first type, kind of the first form we'll look at is called the explicit rule. So we're focusing on geometric sequences, and this part of our notes will be how do we write geometric sequences using the explicit rule. Use a different color, geometric sequence, explicit rule. Okay, so I might have a geometric sequence like the one above, 5, 10, 20, 40. There's a little bit of vocab here. I have an n value, which represents the number of term. So I would say term number 1, 2, 3, 4, and f of n represents the value at that term, the value of the term. So we said 5, 10, 20, 40. So let's do some labeling here. N represents the number of term. So we would say like the first term, the second term, third term, so on. And f of n is the value. Okay. And in this case, since our sequence started with term number 1, we would say that this is the initial term. Okay, so this is an example when the initial term is 1. I'm going to highlight that 1. That's really important. Our initial term is 1. So in this case, in order to write the explicit rule, I would have f of n, which we said was the value of the term, is equal to A. A is going to be the initial term value. Times r to the n minus 1. Okay, where r is the common ratio. And n represents the term number, which we already labeled in the table. So that is the way you write the explicit rule for a sequence if the initial term is 1. Okay, so let's go ahead and write for this one. One last thing we need to note is that in order to identify the common ratio, the common ratio or R is equal to f of n divided by f of n minus 1, meaning a term value divided by its previous term value, okay? So in this case, to find our common ratio, I could take f of 3 and divide it by f of 2. F of 3 divided by f of 2 would be equal to 20 divided by 10. And that's going to tell us that our common ratio is equal to 2, which we already knew. We said that to get to each new term, you multiply by 2, but maybe the common ratio is not so common, and so we could use this formula here. Okay, so now it's just a matter of plugging in our information into this form to find our equation. So we said f of n is equal to the initial term value. So the initial term was 1, its value is 5, times the common ratio r, so 2, to the power of n minus 1. And the reason this is so great, and the reason that we're trying to find this equation, is now that I know this equation, I can find any value in the sequence. So what if I said find the 20th term in the sequence? Well, I could just like keep multiplying by 2, right? But that gets redundant, and I have this equation now. So if I want to find the 20th term, the f of 20 is equal to, just plug in 20 for n. 5 times 2 to the power of 20 minus 1. And all I need to do is type that in my calculator. F of 20 is equal to 5 times 2 to the 19th power. The only thing that's being raised to the 19th power here is the 2, and then you multiply whatever you get by 5. So f of 20, go ahead and type that in your calculator, you will get 2,621,440. Okay. So obviously it's only the 20th term, but being exponential, that value gets really large really quickly. Okay. All right, but something else we need to think about is sometimes you're going to be given a sequence, and maybe this exact same sequence, and instead of the initial term being 1, the initial term will be 0. So over here, I'm going to say that the initial term is 0. 1, 2, 3. And the initial term value is still going to be 5, and then 10, 20, and then 40. But this does change our equation. Our form for this, our general form, will be f of n is equal to a times r to the power of n now, instead of n minus 1. So the way I remember which one is which is you can think of n as n minus 0, representing the 0, and n minus 1 represents the fact that it starts as 1. Okay, so maybe your initial term is 2. We don't really see that much. It's really just 0 and 1, but you would then put to the power of n minus 2. Okay, so how does that change this problem? Well, the common ratio is still going to be the same, but my equation is now, my function to represent the sequence is f of n equals 5 times 2 to the power of n now. And so if I want to find the 20th term, f of 20, that would be 5 times 2 to the 20th power. And if I plug that in to my calculator, the 20th term would be 5,242,880. And if you compare these two numbers, the one on the right is taking the one on the left and multiplying it by 2. So it's one more, it's the next value. So the 21st term over here is the same as the 20th term here. And that's just because we started with a term number of 0. Okay, and when we get more practice here, you're going to see why it's important to recognize if your initial term is 0 or initial term is 1. Okay, so I'm just going to kind of divide these here. And now we're going to look at some examples. Okay. So I have enough room to do it here. Example 1. State the explicit rule for the following geometric sequence then find f of 7. Okay, so one thing that's nice here is they told us it was a geometric sequence, which my sequence is 4, 16, 64. If I was not told that, I should be able to identify that it is geometric based on the fact that to get to each new value, we multiply by 4. Remember, if I couldn't recognize that, I could take a term and divide it by its previous term. We know 64 divided by 16 is 4. Same thing with 16 divided by 4. All right. My initial term value is A, and I'll just go ahead and say that that's term number 1. So f of n is equal to the initial term value, 4, times the common ratio, which is 4 as well, to the power of n minus 1. Since I'm saying n minus 1, then that means that this number 4 is term number 1. Okay, and if really a good rule of thumb here is that if it's not told for us to use term 0, we'll just assume that a general geometric sequence starts with term number 1. And this will make more sense too when we learn like what this looks like with application problems. And we'll see a need for having a term 0 and a term 1. Okay. But we're not done with the problem. It said to find f of 7. So f of 7 means I plug in 7 for n. I'm finding the 7th term in the sequence's value. So f of 7 is equal to 4 times 4 to the 6th power. Plug that in our calculator and we get f of 7 is equal to 16,384. So something that hopefully you are seeing here is that with these geometric sequences, the values of these numbers in these sequences get really large really quickly because we're multiplying to get to the next value. okay? And the explicit rule is really nice because, like you've seen, it helps us find any term value in our sequence, any value of a term in the sequence without having to know the previous term, okay? And that's really nice. Using the explicit rule, I could find the 100th term, the 200th term. I could know all of that, okay? Let's do one more example here. I will clean this up later, but I'm just going to put my example right now so it's on the same page right here. Example 2 is 162, 18, 2, 2 over 9, and so on. So to find, first off, I know A, my initial value is 162. And to find R, I'm just going to take a term value. I'll pick 2, and I'm going to divide it by the previous term value. We get 1/9 is our common ratio. So from that, I know that my explicit rule would be f of n is equal to the initial term. I always remember the initial term goes first because kind of by what it's called, initial term is the initial value in your equation. So 162 times 1 over 9 to the power of n minus 1. We'll assume that 162 we'll say is term number 1. It wouldn't be wrong to say it's term number 0, but we don't really have a reason to say it's that. Okay. And that's all we were really asked to do here. Okay. Well, like I just said, that's really nice that we can find any term value in a sequence. If we are given a sequence of numbers, I can know the 100th term, the 200th term. I can know all of those values. There's also what's called the recursive rule. So now, our notes, we're going to still look at geometric sequences. We're going to focus on how we can represent them with the recursive rule, another equation to represent sequences. Recursive rule. And unfortunately, the recursive rule is not as nice as the the explicit rule. The recursive rule is all about knowing the previous term. Okay, so the general format for a recursive rule is f of n equals the common ratio r times f of n minus 1, where f of n minus 1 represents, go ahead and put like a bracket around this. This represents the previous term. And R is the common ratio. So in order to know f of n, I have to know the previous term to it. And we also have to add in here that when we write this form, we then write where n is greater than or equal to some value, and we say what the initial value is. A is equal to some value, okay? And this will make sense in just a moment where we look at an example. So if my sequence starts with n equal to 0, so n is 0, 1, 2, 3, and f of n is 4, 8, 1632. So you can see that our common ratio is 2. We're going to multiply by 2 to get to each new term. And so my recursive rule would be f of n is equal to the common ratio 2 times f of n minus 1, where n is greater than or equal to 1 and a equals 4. The initial term is 4. So with that n greater than or equal to 1, we're basically saying you can use this rule for values of n that are equal to 1 or greater, because we know the 0 term is 4, and so you can start using this rule for the first term, second term, third term. Okay, that's what that n greater than or equal to 1 means. All right, but what if my sequence started with n equal to 1? How does that change how this looks? Well, my sequence would start with 1, 2, and then go to 3. F of n be I'll still say 4, 8, 16. So I'm still going to be multiplying by 2. So f of n equals the common ratio of 2 times f of n minus 1, representing the previous term, whatever that previous term value is. But now I'm going to say I can use this rule when n is greater than or equal to 2, and I'll still say that the initial term value is 4. So by saying n greater than or equal to 2, I'm saying that this sequence started with a term value or a term number of 1. So I'm saying the initial term with term number 1. So if I know that the initial term value is 4, I can start using this for term number 2. Okay, and so I could plug in 2. I'm going to show you how this works. If I wanted to know f of 2, because that's the first one I can use this for, then that would be 2 times f of 2 minus 1. Okay, f of 2 equals 2 times f of 1. And we know based on here that f of 1 is equal to 4. So I would have f of 2 is equal to 2 times 4, which equals 8. That's how you use the recursive rule. So I found the next term value, and I would just have to keep doing that. Multiply that by 2, multiply that by 2. So it's not as helpful, but it's still really the important thing here is we know how to write it. Okay, it's not going to help us find a lot of values in our sequence, but it is important for as far as notation goes. Okay. So in our last example for our notes today, we are going to be given a sequence, and we need to write both the recursive and the explicit rule. So here we're going to start with term number 0. And we'll start with 0.5, 1.5, 4.5. Keep clicking that eraser. And then 13.5. So if I can't tell what my common ratio is by looking at it, we can take a term value. I'll just take 1.5, and I'm going to divide it by the previous term value. And 1.5 divided by 0.5 is 3. My initial value is 0.5, or I could say 1/2. And now I'm ready to write my rules. Okay, so we have the recursive rule, which is what we just learned. Okay, so the recursive rule is going to be f of n is equal to, it only uses the common ratio in the equation, so 3 times f of n minus 1, or the previous term value, where n must be greater than or equal to, well, if I started with a term number of 0, then n must be greater than or equal to 1 in order to use this rule. And my initial term value is 1/2. You could also see this written as f of 0 equals 1/2, saying that the term 0 has a value of 1/2. So you could see that written that way as well. Okay, now let's make a note about the recursive rule. Think about when the recursive rule can be used. It can only be used when you know the previous term. That's an important note to make here. You can only use the recursive if you know the previous term. Okay, next we'll do the explicit rule. So we're still looking at the same geometric sequence, but we're going to write it using the explicit rule. So both of these can just be considered two different notations to express a sequence. So the explicit rule would be f of n is equal to the initial term value. Always remember initial means it goes first, so 1/2 times 3 to the power of. This started with a term value of, or a term number of 0. So this is going to be to the power of n, kind of like n minus 0. So it's just an n. And what's nice about this rule is this rule can be used to find any term in the sequence. So if I want to know the 50th term, the 100 term, I can use the explicit rule to find that. Okay. And so if I'm given enough information, then I definitely want to use the explicit rule if I'm able to, if I'm needing to find, a term where I don't know the previous term. Okay. All right, so that is geometric sequences and how we can write them using the explicit and recursive rule. All right, so that's the end of our notes for today. Please let me know if you have any questions, and make sure that you also open up your practice today and do some of that practice on your own as well.